guys, here we're in chapter 2 of distributed computing. This chapter deals with interprocess communication. Interprocess communication is a very important part of your distributed computing. So to know what is actually a distributed computing or what is interprocess communication in distributed computing, let us recall what is distributed computing. Distributed computing is something which is performed on a distributed system. Then what is distributed system? Distributed system is a collection of independent computers which are connected together to perform any task. So distributed systems are a group of networked computers which share a common goal for their work. They share memory or they share the program execution space. These systems are called as tightly coupled systems because if they have to share the memory, they have to be connected to each other. Hence, they are called as tightly coupled systems. Here, each processor will have its own private memory. Information, whatever has to be exchanged, will be exchanged in the form of messages. So, the diagram what is shown in the slide here shows that different computers connected through a wireless connection. So there can be LAN connections which is connected together to make a distributed system. There are different systems located in different locations which can be connected together to perform a single task. So distributed computing perform computing or as a network service, or it can perform computing based on network applications. So what is a network service? A service which is provided by a server. A server is nothing but a special kind of program. When it is provided by a server, we call it as a network service. Best examples for these are your email service, your FTP service. You have so many other email services. You have so many network services available. The next one is network application. Network application is an application which runs on a networked computers, which is useful for the end users. It ranges from enterprise applications. It can be like for online shopping. It can be for electronic auctions. It can be for network games. All this come under network applications. So these are the kind of services or applications which is performed in the distributed computing. In distributed computing, each computer has its own local memory and information can be exchanged only by passing messages from one node to another by using the communication links. So each system will have its own local memory, each system will have its own processor. They're going to share thus the source or memory it can be also shared by other systems. But each has their own memory and processors. Distributed computing is a subject which is related with so many other subjects. It has the basics of operating system, it has the basics of software engineering, it has the basics of networks. So all this together will make a distributed computing a particular subject. It has so many branches in it. So next we move on to interprocess communication. So what is interprocess communication? Before that, we have to know what is a process. What is a program? A program is an artifact which is constructed by a software developer using some form of programming language. Or in general, we call it as a program is a set of rules, a set of code. So in a program, what is a process there? A process is something which is an execution. A program which is an execution, we call that as a process. So, and it is inter-process communication. When two processes interact, we call it as inter-process communication. It can be within the same system, it can be between different systems. So, in generally, when it is in distributed computing, we call it as when the processes of two different systems interact, we call it as inter-process communication. Here, more than two separate independent processes interact with each other to collaborate on a task. So this processing or interprocess communication will engage with each other based on a particular protocol which is agreed by both the processes. Protocol is nothing but a set of rules. Inter-process communication is a backbone of distributed computing. As I've said earlier, distributed computing are systems which are interconnected together in a network. So when the systems are interconnected, they have to share a lot of data, they have to share messages, resources, they have to interact. Message passing has to be done. So in such a cases, we have to know how the processes interact. What kind of model exists, what kind of architecture is below the knee. So we have to know how it actually works. So to know that, we have to actually know what is the process and how does the inter-process communication happen in a network. So inter-process communication can happen in different ways. In general, there are three types of communication: unicasting, multicasting, broadcasting. Unicasting is where communication is from one process to single other process. It is just one-to-one communication. You can see in the diagram there where one is interacting with only one. In multicasting, communication is from one to group of processes. That is one to many. One process will interact with many other processes. Third one is broadcast. Communication is from one to all processes in a network. That is one to all. There is a difference between multicast and broadcast. Multicast is one to many, but it doesn't interact with all systems there. But in broadcast, it has to interact, or it should be a one to all system. So only then it is called as broadcast. So these are the types of interprocess communication. So interprocess communication happens with four different operations. There are four primitive operations in IPC. So they are connect, send, receive, disconnect. So in the diagram, it shows the interprocess communication in basic HTTP. HTTP is a network service protocol. Most of the network service protocols are implemented using primitive IPC operations. So here HTTP is basically used in World Wide Web. So a web browser and a web server, how does it interact using these four operations is shown in a particular diagram. So you can see a diagram which depicts where we have a web browser, we have a web server, and we can show the data flow is shown using the arrows. Circles depict what are the operations, and the rectangle shape shows that is a process. So we have C1, C2, C3, C4 and S1, S2, S3, S4. The operations are given onto the right of the figure. So C1 says first what we have to do is to access something from a server, we have to make a connection with it. So C1 is something which is making a connection with the web server. Once the connection is done, the web server has to accept the connection. That is what is given in S1. C1 will make a connection, S1 will accept a connection, then C2 will send a request, requesting for particular kind of service. Then the web server will receive the request. Once the request is received, then it will send the response to the web browser that is given in S3. S3 is sending the response and C3 will request is responding to the response. And C4 and S4 is something which once every work is done, every connection, a service is requested and response is got, we have to disconnect from both the sides. So C4 and S4 is disconnecting. So once everything is done, the work of IPC is done here. So all four operations are used in the interprocess communication. The next is event synchronization. So interprocess communication requires two processes to synchronize their operations or coordinate with each other. That is, the main difficulty with IPC is that the processes involved will execute independently, and both the processes will not know what happens on either ends. In such a case, when one of the process requests for something, the other process has to wait for the accepting of request. So in such a case, if it is not done, there will be a there will be no proper order, there will be no synchronization in the events. So how to achieve the synchronization? That can be achieved by a technique called as blocking. Blocking is nothing but it is a suspension of the execution of a process until the operation issued is completed. So in IPC, we have two kinds, we have classified into two. One is synchronous operations and asynchronous operations. So synchronous operations come under the blocking operations. Asynchronous operations will have non-blocking operations. Blocking operations is something where we are suspending the process until it finishes a particular request. In non-blocking operation, we are not suspending any of the processes. It keeps on doing what its work on both the ends. If process 1 or process 2, they doesn't know what is happening on either ends, but they keep sending the request or accepting the request. Whether the request is received or not, the process keeps on executing. So this is how we are going to classify the operations into two ways, synchronous and asynchronous. So based on the operation, the main operations here are send and receive. So based on these operations, we have classified or we have divided the operations into four scenarios. There are four possibilities of how the execution happens. So first one is synchronous send and synchronous receive. Next is synchronous send and asynchronous receive. This scenario has three other scenarios in it. Third one is asynchronous send and synchronous receive. The last one, asynchronous send and asynchronous receive. The first scenario we are going to study here is synchronous send and synchronous receive. So here both the sides, it is synchronous send, synchronous receive. Synchronous and synchronous means it is blocking. So until a particular operation is fulfilled, the processes will be blocked. That is what we mean by a synchronous term. So this diagram what is shown in the slide says it is kind of a diagram called as event diagram. Event diagrams are used to know the event synchronization of a protocol session. So in this scenario, a receive operation issued causes the suspension of the issuing process, that is the process 2. Until the data is received, it will be the process will be blocked. In the other end, a send operation issued causes the sending process, that is process 1, to suspend. When the data has been sent is received by process 2, the IPC facility will send an acknowledgement to the system 1. That is, it has got the message, it has got the data, or it has received the data. So in process 1 will be subsequently unblocked. So this is how it happens in your synchronous send and synchronous receive. The use of synchronous send and synchronous receive is warranted if the application logic of both the process requires that data sent must be received before the further processing. So here it has to be like, if next processing has to be done, both the processes should be unblocked. And to both the processes to be unblocked, the data sent or the data received should be known to each other. The acknowledgement should be received by both the ends, process 1 or process 2. And this is how your synchronous send and synchronous receive work. The next is synchronous send and asynchronous receive. Here, the process 1 is in blocking state and the process 2 is in unblocking state. That is when the data has been issued, when the data has been sent or the data has been received. How does the two processes in which state the process belongs to? That is, the process 1 will have to wait for the data to get back, but in the process 2 it need not wait for any kind of operation to be fulfilled. That is what the word term asynchronous mean. An asynchronous receive operation causes no blocking of the process and the outcome will depend on the implementation of IPC. So in this asynchronous receive, there are three scenarios. So in three scenarios, it will act in three different ways. So in this case, the data is delivered to the process 2 immediately and an acknowledgement from the process 2 or the system 2, system 2's IPC facility will be known to it'll be given to the process 1 and it will block or unblock the process 1. So what happens here is, since when the data is received, it will get to know that the data is received, and it will send an acknowledgement to the process 1. Once the acknowledgement is received, immediately the process 1 will be unblocked. This is what is in scenario 1. In synchronous send and asynchronous receive in scenario 2, here also the process 2 will be in unblocking state, process 1 will be in blocking state. But what is the difference between scenario 1 and scenario 2 is, scenario 1, once the data is received, the acknowledgement will be sent to the process 1. But in scenario 2, here the process 1 will be blocked indefinitely until process issues a receive request. And an acknowledgement eventually should arrive from a host 2's IPC facility. So here there is no acknowledgement sent from process 2 to process 1. So if the acknowledgement is not sent from process 2 to process 1, the process 1 will be continuously in a blocking state. It will not get to know what is happening on the other side. So this state is what we call it as indefinite blocking. The data requested by the receive operation has not yet arrived on the process 2. So in such a case, the process 2 also will not try to interact with process 1. So in such a case, what we have to do is we have to re-request the process 2 to send the data back. So the re-requesting, until the data has been received by this process 1, the continuous request has to be done by process 1. This continuous request is called as polling. The polling is a technique which we have used in the scenario 2. The continuous request of data from process 1 to process 2 is done in scenario 2. Once the data is or the acknowledgement is got back, then the process 1 will go back to the unblocked state. If the acknowledgement is not got, it will be continuously in the blocking state, or we call it as indefinite blocking. The next scenario is a scenario 3 of synchronous send and synchronous receive. Here the scenario requires the process 2 to provide a listener or event handler that can be invoked by the IPC facility to notify the process of the arrival of the requested data. That is, in process 2, since it does not get to know when the data has been received, so we keep an event handler to check whether the data has been received or not. So once the event handler gets to know the data has been received, it will notify the IPC. Then the IPC will send an acknowledgement to the process 1. Once the IPC sends acknowledgement, then the process 1 will return back to its original state or its unblocked state. Until then, it will be in a blocking state. The last scenario is synchronous, asynchronous send and synchronous receive. Here, both the receive operation issued will cause a suspension of the issuing process until data is received to fulfill the operation. The send operation which is issued will not cause the sending process to suspend. So here process 1 is asynchronous, process 2 is synchronous. Hence, the process 1 will be in a non-blocking state. It will keep sending the data. It will not wait to get the response. But in the process 2, it will keep waiting for receiving the data or receiving the request. Hence, the synchronous 2, that is the process 2 which is synchronous, will be in the blocking state until it issues or until it receives the request from the process 1. The last kind of scenario in the send and receive operation is asynchronous send and asynchronous receive. Here, as the name says, asynchronous send and asynchronous receive, both the sides process 1 and process 2 are in non-blocking state. Since both are in non-blocking state, they do not care of what is the request done, or they do not care of what is the response done, because they don't wait for whether the request has got or received a response is done or not. Here, without blocking on either side, the only way the data can be delivered to the receiver is if the IPC facility retains the data received. That is, if the process 1 has sent the data to the process 2, The process 2 will not even care of whether the data is received, but there is the IPC facility in the system which has to note whether the data has been received or not. If the data has been received, it will send an acknowledgement to the process 1. Even in the other side also the same thing happens. The process 2 will send, if even though it sends a response back to the process 1, the process 1 will not keep waiting for the process 2 to get the response. It keeps executing the other kind of, it keeps executing, it doesn't block the process from execution. So that is where both the states, both the processes are in unblocked state. The next concept is timeouts and threading. So we have been introduced to what is blocking now, which we have studied in the previous slides. Blocking is something which is suspending the process from execution. So blocking provides the necessary synchronization for IPC, but it cannot be acceptable when we say that when there is indefinite blocking. If the process execution is an indefinite blocking, it has to go into the normal state, it has to be unblocked. So for that, what has to be done? So there are two kind of issue. This issue can be solved using two kind of measures. The first one is using timeouts, or it can be used using threading. So what is timeout? Timeouts is something where you set a maximum time so that a process can be in a blocking state only till a particular kind of particular time. So timeouts are provided by the IPC facility and may be specified in a program within an operation. If any process goes into indefinite blocking, we are going to fix a particular time. For example, if we say 10 minutes of time, if a process is in blocking state for 10 minutes, after 10 minutes, it will come back to your unblocked state because of the time mentioned in the program. So that is how we can make a process 1 or process any process from the blocking state to the unblocking state. The next one is the threading concept. Threading is nothing, a thread is nothing but a single sequential flow of a program. It is called as a lightweight process. It takes actually a less time for creation of a terminating from a main process. So if multiple threads can perform multiple tasks in a single program. So by creating a thread, we can, instead of blocking a process, we can create multiple threads, multiple smaller parts of the program and execute it differently. We need not block the process from its execution. So that is where we use a thread. So program will spawn a child process, or we call it as a thread, to issue a blocking operation, allowing the main thread or a parent process of the program to proceed with the other processing, while the child process or the child thread is suspended. So instead of blocking the main process, we call a thread and the blocking state will be in the thread. But the main process will keep its execution and it will not be blocked. That is how we can solve this issue of blocking or indefinite blocking using two concepts, timeouts and threading. This diagram shows how the timeouts and threading work. So we have the time arrow mark given, that is the time given for a particular process to be in block state. The other one is a process where we have created, it is a main thread and we have created a child thread. So the blocking operation, whatever happens, will be in the thread, but the main process is not in a blocked state. It will keep its execution. So the blocking, whatever happens, will be in the thread. Once the thread is gone back to the unblocked state, it will return back to the main process. So once it returns back to the main process, so both thread will be terminated and the process will continue its execution. The next is deadlocks and timeouts. Deadlock is also related to indefinite blocking. Indefinite blocking is also caused by a deadlock. The deadlock might be a result of, like, when a process or a thread enters a waiting state, the deadlock occurs. How does it occur? It is a result from operations where the operations are, if it is not issued properly, if there is a misunderstanding of a protocol, or if any related to any programming errors. In such a case, the deadlock occur. Deadlock occurs when a process or a thread enters a waiting state because a requested system resource is held by another waiting process, or which in turn is waiting for another resource held by another waiting process. And there are multiple processes interacting or requesting for each other and waiting for each other, then in such a situation we call that situation as a deadlock situation. So it will cause, or it will make a process to go into indefinite blocking state. To relieve that from indefinite blocking, we use the concept of timeouts. So timeouts are given for each process during issue of a event. When a particular time is given, after the time, any process cannot be in a unblocking state. It comes back to a unblocked state. That is what is shown in the diagram in the slide. So we have process 1 which is receiving from process 2, and process 1 is blocked until it receives data from process 2. And we have process 2 which is receiving from process 1. It is also blocked because it has to receive from process 1. So both the processes are receiving from each other, no one sending to each other. So hence both are receiving from each other, there is no one to send data here. Both the processes keeps waiting for some response from each other. Since none of them are sending the data to each other, both the processes will be in a blocked state. To relieve them from blocked state, we use the concept of timeouts. So the next concept here is event diagram. What is the use of event diagram? We have seen what is event diagram when we have explained about synchronous send, asynchronous receive. The diagrams, whatever we have used there is nothing but a event diagram. So then, what is event diagram? It is a diagram which is used to document the detailed sequence of events and blocking during the execution of a protocol. So this example which is given is for a request response protocol which has two processes, process A and process B. And here the execution of each process with respect to time is represented using a vertical line. With time increasing downwards, it will say how the process are executing. A solid line shows how execution, it is like an execution line. It represents a time period during which the process is active. A broken line, that is a dotted line, interval represents when the process is blocked. So in the beginning, both the processes are active. When the process B issues a blocked receive operation, the process 1 goes into the blocked state. So that is when any issue or any operation has to be fulfilled, till then a process will be in a blocked state. So there is we have two kinds of operations here. Each round of request response has two pairs of operation like send and receive. So any number of send and receive operations can happen during this event during the complete execution of a program. That send and receive operations are depicted using this request and response. So when the process A is requesting for the process 2, it will enter the blocking state. And once the response is sent back to the process A, it will come back to its unblocked state. And the process 2, until it gets the request, it will be in a blocked state. Once it gets the request, it will go back to its unblocked state. So event diagram is specifically to know the sequence of events, how the send and receive operations work. The next kind of diagram here we are going to study is sequence diagram. Sequence diagram is more commonly used to document inter-process communication. It is only thinking about how the send and receive happens. It doesn't consider whether this process is in blocking state or unblocking state. The execution flow of each participant of a protocol is represented as a dashed line, and it does not differentiate between the states of blocked and executing. Each message exchange between the sides is shown using a directed line, that is using an arrow mark. So here it says that process A is requesting process B and process B is responding process A. Only the inter-process communication, that is send, receive. Only this is noted in the sequence diagram. Other than that, it doesn't say whether it is in a blocked state, unblocked state, or process has been stopped from execution or not. To detail the sequence of events of inter-process communication, we use sequence diagram. Now we have studied what is IPC, what are the different kinds of operations we have used in IPC, and how the event synchronization can be achieved using timeouts or using how the blocking states. And thus IPC to be achieved by a programmer, he should adapt to different models, he should adapt to different paradigms. So using different paradigms, IPC can be provided to a programmer who wishes to adapt it in a particular system. So thus paradigms can be differed in different ways. We have different kinds of paradigms, and we have this paradigms can be implemented in different ways. So some of the best examples here is one is using data transmission. That is, whenever we use serial transmissions, parallel transmission, we use this data transmission paradigm, which is which is in the lower level of abstraction. It comes in the lower level. Next, we have socket APIs, where we can use it in WinSox, Unix. We use the socket APIs, where the transmission happens into different connectionless and connection-oriented ways. The higher level of abstraction is remote procedure methods or remote procedure calls, we, which is very popular in these days, which is used in most of the applications. The Java applications, Java RMI, use this kind of paradigms. So we are going to learn in detail about all these paradigms in the next chapter. This is just how the level of abstraction is and how the systems have the paradigms have evolved from IPC. So for the purpose of IPC, there is different paradigms which has been developed, and these paradigms are used based on the level of abstraction, which has to be learnt or which will be learnt in detail in the next chapters. And this is all about your IPC interprocess communication and what its operation.